All right, in this video, I'm going to go over the big ideas from the Windmill lab. These questions here you should be able to answer. So if you want to test yourself and see if you understood everything, pause the video now. If you can answer all these questions, you're in a good spot. Moving on. Rotational inertia or rotational mass. This determines how hard it is to start or stop an object from rotating. So it's how hard it is to angularly accelerate an object. It's determined by four things. I'm going to go through them real quickly here. It's the shape of the object. Remember we said shape is also called distribution of mass. These two things have different shapes. This is a hoop. This is a disc. Okay? These have different shapes. This is a solid sphere. This is a hollow sphere. This is a solid sphere. You can't tell, but that's what they are. So distribution of mass is shape. Distribution of mass is not a thing that is ranked or bigger or smaller. It's not like it has a big distribution of mass. The mass is distributed close to the axis of rotation or far away from the axis of rotation. The other thing is distribution of mass can be for individual pieces of mass. This mass here is close to the axis of rotation. This mass here is farther away from the axis of rotation. So that we wouldn't call shape as much, but when we get to these objects, we call it shape. The mass itself, more mass, harder to angularly accelerate, more rotational inertia. The size of the object, same shape, different size. Bigger size, harder to angularly accelerate, more rotational inertia. And lastly, our choice of the axis of rotation. So this can kind of change the size of the object, put more of the object further from the axis of rotation. So here's a great example. I can take this meter stick and try to kind of rotate it this way. But if I rotate it this way along this axis of rotation, it's really, really easy because all that mass is really close to the axis of rotation that runs down this way. But if I do it this way, put the axis of rotation down here, the mass is really far away. I didn't change the meter stick at all. I just changed the axis of rotation. But primarily, the rotational inertia of an object is determined by the physical properties of that object, but also where we choose to put our axis of rotation. All right, on to the equations. So this is the equation that you developed in your lab today. That slope we were looking at, we realized that the bigger the slope was, the easier it was to angularly accelerate, and that kind of was counterintuitive to our first semester when we had more mass is harder to accelerate. So we said more rotational mass should be harder to accelerate and less rotational mass should be easier to accelerate. So if I look at this here, I have torque net equals I alpha or alpha equals torque net over I. This is a little bit better for thinking about things conceptually, cause and effect. Net torque affects the alpha. And then this, a lot of times, this is the way we will write it. So when I give you a graph and I say if it's torque on the y-axis or it's angular acceleration on the y-axis, you have to do that kind of linearization and match up with the equation to see what the meaning of the slope is. All right, to calculate rotational inertia, you could guess the equation based on the units of rotational inertia. It's mr squared, and that's like for a point mass. So if I wanted to get the total rotational inertia of these four masses, I do mr squared for this, where r is the distance from this mass to the axis of rotation. Let's see, can I do that? Then I do mr squared for this one, mr squared for this one, and mr squared for this one, and they may not be the same r. It's a different distance, and that's okay. But I could add them all up. They do not balance out. So if I have one here on this side and one here on this side, the same thing, it's not zero. They don't cancel each other out. It just adds up. Then, if I don't have a point mass, if I have a shape, some shapes are easier. This one's easy. All this mass is the same distance from the axis of rotation. Okay? So I have all this mass is the same r from the middle. So mr squared, the total m times this r. It's one r value. This one here is much more of a problem because there's some mass that's on the axis of rotation. There's some mass that's a little bit further, a little bit further, a little bit. So we have to do a summation. Kind of like what we did for the windmill, but I got to do this mass mr squared plus this mass mr squared plus this mass mr squared plus this mass mr squared over and over and over and over for everything. That's a pain in the butt. What's even worse is something like a sphere, and we'll talk about that later, why that's more difficult. So I'm not going to actually have you do that summation. You can do this with calculus and kind of figure out what the answer is. But anytime you have this shape, it's just mr squared. And if I wanted to go from the hoop to the solid disk, I would take pieces of the hoop and I would push it in towards the center, right? I would take some of this mass and push it in if I wanted it to be all equal. If I'm pushing mass in towards the center, I'm reducing the rotational inertia. So if these have the same mass and the same size, this would have less rotational inertia because some of its mass is closer to the axis of rotation, where all the mass on this one pretty much is the same distance away. It'll always be less, so this less than this. So a shape, solid sphere, hollow sphere, solid disk, whatever, is going to be less than mr squared because some of the mass is closer to the axis of rotation than the hoop. So the equation will be some fraction that's less than 1 times mr squared, and we'll give you that equation. We'll tell you what it is. So for this one, it ends up being a half. You won't have to memorize that. It's 1/2 mr squared. You do m of the disk, and then where that r, that capital R there, is the size of the disk. That's the actual radius. It happens to be the actual radius. For a solid sphere, I can't remember. 3/5 or 2/5 mr squared, something like that. For a hollow sphere, I think it's 4/5. We will tell you that though. So it's some fraction based on the shape of the object. Okay? All right, that's a quick overview of what we did in class, whether you missed it or you just wanted a little review. Hopefully that was helpful.